Hi everyone, welcome back to our video lecture on numerical analysis. In the previous lectures, we have discussed about finding the roots of various functions. Also, we have found the method of interpolations. Now, in today's lecture, we will be discussing about differentiation. So, we know that derivative is the instantaneous rate of change. But practically finding the derivative of a function is not as easy as we think, because if some vehicle is moving, you will get a data set at particular time t, its position or displacement is this much. At another time t1, its displacement is s2. Like that you will get a table. From the table, how will you come to the function? There your interpolation is required. So here we are going to use the interpolation idea to get the derivative directly. Let us see how we are going to do this. Given a table of values x0, y0, x1, y1 up to xn, yn of a function y equal to f of x, we want to find the derivative of the function at various points. In similar case, earlier in interpolation, we were trying to find the approximate polynomial to f of x. That means we use this data set to construct a polynomial which is the best approximation for the function f of x. There are various methods to find such polynomial. Here, let us look into Newton's forward interpolation formula. To find the value of the function at x, we will be using y0 plus u delta y0 plus u times u minus 1 by 2 factorial delta square y0 up to the nth order, where x is equal to x0 plus uh. This Newton's forward interpolation formula is left hand side is in the variable x, but on the right hand side the variable is u, because there is a relation between x and u. So if you want to find dy by dx, you want to differentiate the right hand side applying chain rule. Also, you may require the derivative du by dx. So dy by dx will be equal to dy by du times du by dx, and du by dx will be equal to 1 upon h. Now applying this, we will get dy by dx is equal to dy by du times du by dx, which is equal to 1 by h delta y0 plus 2y minus 1 divided by 2 delta square y0 plus 3u square minus 6u plus 2 divided by 6 delta cube y0, continuing like this. If you want to evaluate this function at x equal to x0, the formula we can simplify. X equal to x0 plus uh, and when you substitute x equal to x0, u will be equal to 0. When u will be equal to 0, the formula will reduce to 1 by h delta y0 minus half delta square y0 plus 1 by 3 delta cube y0 minus 1 by 4 delta to the power y0 plus etc. The signs will alter. Now let us see a particular problem. We want to evaluate dy by dx at 1.2 from the given table. Similar to Newton's forward interpolation formula or backward interpolation formula, we can construct the table, forward difference table of this given data. This will be the forward difference table. And here you take x0 equal to 1.2, then y0 will be 3.3201, delta y0 will be 0.7351, delta square will be 0.1627, delta cube will be 0.10361, delta 4 y0 will be 0.0080, and delta raised to 5 will be 0.0014. Applying in the formula, we will get the value of derivative at x equal to 1.2 as 3.3205. You can try this exercise yourself. Using the Newton's forward interpolation formula, you can find the second order derivative. The same thing you can try with Newton's backward interpolation formula also. From the previous problem, here you have calculated dy by dx at 1.2. Use the same data to calculate d square y by dx square at 1.2. Now the third problem, at different times t in seconds, angular displacements in radians are given. You are supposed to find the angular velocity at t equal to 0.06.